warm morning to everyone present here, and here we are with the first Feynman talk of the session. And I'm honored to invite Professor Madhavan Varadarajan, former director in charge at the Raman Research Institute, Bengaluru, for today's Feynman lecture titled A Black Hole Story. Today we are delighted to listen to one of his recent works which aims to study black hole evaporation and Hawking information problem loss. With that, I warmly invite Professor Madhavan to deliver the talk.
Yeah, so time is short, so I don't think I'm going to be able to ever get to Hawking evaporation. I just go on, and at 12:30 I'll stop. Okay, so that is the formula. And as I said, I don't know who came in late or whatever, but just relax. Okay, no tension. Whoever wants to go, whenever for another talk or for something, just go. Alright, I will stop at 12:30, then the next batch of people come in and I'm kicked off. Okay, so just relax and have fun, because it's going to be a fun talk. It's not going to be anything else. So what I want to do in this talk is to tell you about the really fascinating developments in our understanding of black holes, together with an account of some of the perhaps even more fascinating personalities who are involved in these developments. And the perspective will not be on black holes as astrophysical objects, with accretion disks or what astronomers see, etc. Rather, it will be in their role as solutions to the equations of general relativity, which is our current very accurate theory of gravity. So before I start, let me just say a couple of words about the conceptual structure of general relativity, because many of you probably have not encountered the theory itself, and it's very different from all other theories, which is why it's so beautiful. So let me say a few words about that before I start on the talk proper, and whichever way you like it. I think if there's some obstruction to further understanding in the talk, stop me. If there are questions which are tangential, then I can take them later, and I'm around till probably till around 4 o'clock. I'll be around. So Newton's theory you're all familiar with. So how does Newton describe gravity? So let's take the example of the sun and the earth. The earth, if the sun was not there, according to Newton's laws, would just move in a straight line. But it actually curves and moves around the sun because the gravitational force is exerted by the sun on the earth, and it moves it away and travels on a curved trajectory. So that is Newton's picture. Einstein's picture, the conceptual structure of Einstein's theory of general relativity, is completely different. So what Einstein says, he describes the same phenomenon, but he says that what the sun does is, instead of exerting a gravitational force, the sun curves the geometry of space and time around it, and the earth tries to move as straight as it can on this curved geometry, so that it looks to us as if the earth is traveling on a curved path. Okay, so for weak gravitational fields, and by weak, weak is always what is weak, right? What are the numbers, etc. So for terrestrial gravitational fields, most astrophysical gravitational fields, Newton's theory is extremely accurate. And of course, Einstein's theory is a better theory than Newton's theory. So it agrees with Newton's theory in this domain. But when the gravitational fields become even stronger deep inside black holes, not necessarily around black holes, but deep inside black holes, or right at the beginning of our universe, or in more, maybe neutron stars and so on, right near the surface of a neutron star. So in those cases, one really finds that there are departures from Newton's theory's predictions, which are pretty significant, and Einstein's theory is the real theory. So if there was time, I could tell you, about the GPS and why Einstein's theory and the curvature of space and time is actually important for the accuracy of your GPS. So it's not fiction, it's real, and we shall just take it forward as the theory which is, to our knowledge, the best of our understanding. Okay. So let me, before I just as a warm-up, I'm assuming that most of you know special relativity or have at least some familiarity with it. Is that correct? If it isn't, then somebody say no. Nobody's saying no, so I will assume familiarity. So, in special relativity, nothing can travel faster than light, and so a very important part of special relativity geometry is the object called the light cone. Right? Now, the space-time structure in special relativity turns out, in a technical sense, to be flat. So the simplest structure, it has no curvature because there is no gravity involved. It's the simplest structure and it's flat, and you'll learn more about it, if and when you do general relativity. So in this flat space-time, I've drawn what is called the light cone, and I've just suppressed one dimension because I can't draw in 4 dimensions. So we have x and y and t as inertial coordinates, and then you can see that if I take any point p over here, right, then I've just rescaled coordinates so that light travels on 45 degrees lines. Okay, so actually this should be c times t. I've just got written c over here. So light travels on 45 degrees lines, and then if you go inside the light cone, right, and look at points over here, they traverse less space in more time than light does. Right? So that means that those guys can be reached by signals which are traveling at speeds less than that of light. That is physical signals. If I look at points outside the light cone, what is called the light cone, over here, then points over here, you simply, if you were to influence points over here, you would have to set signals which are faster than the speed of light, which is not possible, and Einstein's theory tells you it's not possible. So, if I look at this point, then all points which it can influence are either on the light cone or within the light cone. And all points which can send signals to it are within this past light cone or on the surface of this past light cone. Okay, is that clear? And therefore, the geometry of space and time also tells you about what is called the causal structure. Which points can influence which other points, and this is extremely important for what I want to say about black holes. Now, what happens in a black hole spacetime? So, in the flat spacetime of special relativity, the light cone structure is the same everywhere. Okay, so, if I rigidly translate in x or t or any inertial coordinate or any combination thereof linearly, then the light cone structure is the same everywhere. It doesn't, because the spacetime is flat. When the spacetime is curved, the light cone structure in one point in spacetime need not be the same as the light cone structure at another point in spacetime. So it could, the light cones could swirl around, from one point to the other and move in strange ways. And in particular, a black hole spacetime is one in which these light cone, so here, at every point one has a small, you can think of a small light cone at every point, okay? And any signal, if you look at a signal near that point, it has to be within the local light cone. Because even in general relativity, nothing can travel faster than the speed of light. Okay, so that is the rule. You have a light cone at every point, and a signal can only travel within that light cone, okay? And wherever that light cone points, alright? Now, a black hole spacetime is one in which all these different, swirling light cone structures are such, they all conspire in such a way that there is an interior part of spacetime from which light cannot get to the exterior. Okay, so whenever that happens, you say there is a black hole, and this interior region is called the black hole region. Alright? So that is what a black hole is. It's intimately related to what signals can come out from there and what signal. And so in a black hole case, nothing can come out, right? So that's why it's black. Even light cannot come out, so it's black. Things can fall in, so it's a hole, and that's why it's called a black hole. Okay. So let's look at in a little bit more detail at the black hole light cone structure of. In this case, it's a spherically symmetric black hole. which has been around for a long time. So everything has settled down, its geometry has settled down, and we are looking at it at very late times. And again, I can't draw it in 4 dimensions, so these circles are supposed to be spheres, alright? Surfaces of spheres instead of circles. But I can't draw surfaces of spheres over here, so I'm drawing circles. So what happens to the local light cone structure, right? If you're very far away from the black hole, then the gravitational field is almost 0. The light cone structure is pretty much the same as in flat space-time. So that's what, it's over here, and so the light cone structure is somewhere over here. And here you'll notice that there are light rays which move away from the center, right? And there's some light rays which will fall towards the center, right? But otherwise there is nothing crazy about it. But now as you go towards the center, it's all spherically symmetric, so the center is a preferred point, right? As you go towards the center, what happens is that the light will start tipping, alright? And remember, you can only be within a light cone, right? Otherwise you have to travel faster than light. But the curvature of space-time is such that the light cones start tipping. And they tip more and more and more. And you can see what happens is that when you go inside, right? Inside this thing, which I'll tell you about more, and you look at the light cone over here, right? Everything inside the light cone is now falling inside, right? Because the light cone itself has tipped. So all the light rays and all signals which can be emitted all fall in the inside, and in fact they all terminate in a point or in a place over here, which is called the black hole singularity, where the gravitational force just blows up. In Einsteinian terms, the curvature just blows up. Okay, so it's a very violent place over there, and everything just ends. You end your light signals. Everything ends their life at the singularity. Alright? So that is what classical general relativity tells you. And as you go towards the black hole and things are tipping, you find even outside over here that there will still be rays which come out, and there will be still rays which fall in, until you reach this point over here, where you just tipped in such a way that of course there are rays which fall in, but they are just rays which kind of can't make it out. They neither fall in nor do they go out. Okay? So these are a bunch of light rays which just stay there. Okay? And their path defines something which is called the event horizon of the black hole. Okay? It's like the boundary between the outside of the black hole and the inside of the black hole. Right? And in this diagram you can see that since these circles actually, you should think of them as spheres, right? The horizon is a 3-dimensional thing, right? Here it's 2-dimensional, right? Just the same, it looks like a cylinder over here, but that's a 2-sphere, a 2-dimensional spherical surface times the real line, right? So it's a 3-dimensional object, and it has these cross sections which are 2-dimensional and spherical, all right? And this is important for what we'll see later. Right? The area of these, well, I don't know whether we have a chance to see it later. We probably won't have a chance to see it later. But anyway, I will refer to them at least in the conclusions, because I'll have to wind up very quickly. Now, okay, this is all very good, right? You have these geometries which are possible geometries, right? But are they really solutions to your equations? So what are these equations which govern the behavior of the gravitational field or the curvature? Well, in Newton's theory, we know that they are the Newton's equations, and they relate the gravitational field to the distribution of matter in space. Right? That's how you compute the gravitation. Similarly, in general relativity, the Einstein equations relate the curvature of the geometry to the energy and matter content in the space-time. Alright? So just similar to Newton's theory, instead of gravitational force, you have curvature. Now, Einstein had his theory of special relativity in 1905 or so, and it took him a decade-long struggle to come up with his theory of general relativity. And this theory is extremely complicated. If you look at its equations, they are much more complicated than Newton's equations. They are like what we call complicated, non-linear coupled partial differential equations. Okay? And it is like, it's impossible unless you study them long and hard, and very special cases you can perhaps get solutions. In fact, Einstein himself couldn't find any solutions to his equations when he got them. So of course, I mean, he was amazing. So he looked at approximate solutions and tried to extract physics from those equations, but he just couldn't find any exact solutions. But just like 6 weeks or so after he found his theory, the first exact solution of his theory was found, and it described exactly the exterior region of the black hole. So that diagram which I told you, everything outside the horizon is what was described by the solution. And this solution is called the Schwarzschild solution, and it's named after an absolutely amazing guy, Karl Schwarzschild, right? So this talk is nice because I can conclude it after this story as well, or I can conclude it after the next story or after the next development, right? So and I'll be around, so I can give a continuation next time I can talk. So this guy was amazing. He was actually, when he found this, he was in the artillery division of the German forces fighting the First World War. Right? So why did this happen, and how did this guy, he was a lieutenant in the army, do something which Einstein himself, after producing these equations, could not do, and he did it in 6 weeks. How the hell did he manage to do this? So Schwarzschild was, the family history says that he was a really, really cheerful guy. Very upbeat, very cheerful, and this will play an important part in the story. And already, in his 20s, mid-20s, he was a very famous astrophysicist. Okay? In fact, Chandrasekhar, I think in the obituary, Eddington's obituary, you must have heard of Chandrasekhar and Eddington and all the clashes and so on. And Chandrasekhar's, so there's a quote, Chandrasekhar says that posterity may rank Eddington next to Karl Schwarzschild as the greatest astronomer of all time. Okay, so this guy was no small fry. Huh? He was really, and he was, he was involved in actually the making of telescopes, telling people to grind lenses. He was one of the pioneers of what is called, diffraction techniques in astronomy, trying to separate images or overlapping images of stars using diffraction gratings. So you commission gratings. On the one hand, on the other hand, he knew all sorts of physics. He was extremely versatile. In fact, there's a quote from an address which he gave later on in his career, which it's a wonderful quote. He says, "Mathematics, physics, chemistry, astronomy march in one front. Whichever lags behind is drawn after. Whichever hastens ahead helps others. I may count it well that my interest has never been limited to things beyond the moon." Okay, so he was a really amazing guy. And in 1901, at the age of like 28 or something, he was given charge of the observatory at Göttingen. And at Göttingen, there were all sorts of people in the department, not in the observatory, but obviously he must have overlapped with all these guys. So there was David Hilbert, the famous mathematician. There was Minkowski, and like this BSP visiting summer program. Paul Ehrenfest came, one of the big guys in quantum mechanics. I think he took a summer course or a few lectures from Schwarzschild. So it was a very vibrant place. And this was in 1901. In 1900, Schwarzschild wrote a paper where he calculated the curvature of space, if space was a hyperboloid or if space was a three-dimensional sphere. Now this was in 1901, even before Einstein's theory of special relativity in 1905. So what was going on, because Einstein himself didn't know differential geometry, which is the mathematical tool relevant to defining and computing curvature and writing down his equations. In fact, Einstein had to learn all this from his friend Marcel Grossmann, who was a mathematician. So how the hell did Schwarzschild come up with even an idea of computing some curvature, right? So this is truly amazing. This was in 1900. To understand this, you have to go back 50 years. So 50 years ago, coincidentally in Göttingen, Schwarzschild did this when he was in somewhere in Munich, but in Göttingen, the University of Göttingen, there was this one of the greatest mathematicians who ever lived, Gauss, and Gauss had just finished his work on the geometry of two-dimensional surfaces, and he had this amazing student, Riemann, who generalized Gauss's work to any dimension. And there is a very famous address by Riemann called, I think, On the Foundations of Geometry, somewhere in the mid-1800s, where Riemann says, well, perhaps space could be curved, and perhaps there is a physical mechanism as to why space should be curved. And this is like, way before Einstein. Okay, so ideas come, and his ideas are very influential. Riemann's ideas, and within the German scientific community of that time, and this is how probably Schwarzschild picked this up. And you can see that one side he was making diffraction ratings, asking them to make them, and then on the other side he was doing the sophisticated mathematics. They were just completely amazing characters. Okay, so then what happens? What happens is that in 1910, at the age of like 36 or so, Schwarzschild is given the highest accolade of being assigned to take over charge of the observatory at Potsdam in Germany. 4 years later, the First World War breaks out. Schwarzschild is 40 years of age. Okay? There's no reason, he's not going to be drafted. He's too old. But out of a sense of patriotism, the guy volunteers to fight in the First World War. Now, he's assigned to the artillery unit as a lieutenant, and because of his mathematical abilities, so he doesn't fight in the trenches, but he's very much in the theatre of war, very close, and he's tasked with computing the trajectories of artillery shells. Okay, so he's sent first on the western front to France and to Belgium, and then finally to the eastern front, which is, that was totally, static, and a lot of fighting, and so on, and so on, and so forth. So this was 1914, right? 1914 goes around, and then I think there was communication with Berlin, right? 1915, a package comes from Berlin. Schwarzschild opens it, and there is in mint condition the first version of Einstein's theory of general relativity. So he opens it, and as I said, within 6 weeks, he has the first ever solution of Einstein's equations which describes the exterior of the black hole. And in fact, there's another, so he writes a letter to Einstein. And just, look at the people. Those days, they are fighting for credit and, saying, oh, I did this first and blah, 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 blah. Einstein gets Schwarzschild's solution, and then he presents it on Schwarzschild's behalf to the Berlin Academy or whatever of Sciences, and so it eventually gets published. And Schwarzschild writes a beautiful letter to Einstein, right? Where, so this is what he says. The war treated me kind enough, in spite of the heavy gunfire, to allow me to get away from it all and take this walk into the land of your ideas. It's just amazing, right? So there's all this gunfire, this, that, and the guy is, calculating stuff. Not only that, at the same time, he's suffering, so he's an Ashkenazi Jew, and in that community, due to the limited, gene pool, and within each other, they were particularly susceptible to an autoimmune disease of the skin, and he contracts that. and it's terrible. It's a disease where the skin starts mistaking itself for a foreign object and starts eating itself. And there's no known cure for this. So he is dying. He's surrounded by gunfire, and he produces not only this paper but 3 papers. One is the exterior solution of the Schwarzschild solution. There's another general relativity solution of a spherical homogeneous mass. And then of all things, he writes a paper on an explanation of what is called the Stark effect in quantum mechanics using the Bohr-Sommerfeld rule. I don't know how he does it, and I'm rusty on the Stark effect myself, but I mean, just like imagine, I mean, the guy, right? So, I don't know, when you complain maybe that you have to take some, I don't know, some metro to planetarium, or your coffee is cold, or at our level that, this really, policies are horrible. And you look at this guy, I mean, just totally amazing. So I really wanted to share this story with you because he's such an inspirational figure, right? And that's where the cheerfulness and all that comes in. He's cheerful. And of course in 1915, 16, he was discharged from the army and then he passed away. Okay, so that was the first story. And let's go on. So the solution which Schwarzschild found was appropriate to the gravitational field of a point mass. So, in order to be taken more seriously, you'd like solutions for more sensible distributions of mass, which collapse under their gravitational weight and then give you a black hole spacetime. So, now such a solution was looked for actively by Oppenheimer. So you all seen the movie Oppenheimer, right? So same Oppenheimer with his student Schneider found a solution for a spherically symmetric distribution of dust which would collapse under its own weight and form a black hole. Okay? This was in 1939, and if I guess you know your history better than I do, 1939 was when the Second World War started, and all the accent moved to nuclear fission. And so while Oppenheimer, if he had continued, he would probably have generated a lot of fantastic work on black holes. It just cuts off because the rest of his life is, all about this thing. But before Oppenheimer in 1939, there is a very enigmatic character in this story whose name is Dat, or Dat, and it's spelled D-A-T-T. And this guy finds this Oppenheimer-Schneider solution in 1938. Now, his paper appears in some Berlin German journal. Okay? And if you look at the, it says B Dat, and then there is some anglicized spelling of Calcutta, like I can't reproduce it over here, and that's it. So we don't know where this guy was from. There has been a technical appraisal of that paper later in one of the journals, much in the 90s or so, by eminent relativists, and it was clear that Vishweshwar Dutt did not really understand what his solutions described. So he had some solutions to some equations. There were some known solutions, already known, and there were some unknown solutions. One of them was this Oppenheimer-Schneider one. But he was not looking for black holes. He didn't understand the import of his solution. And in general relativity, it's very important not only to just have some solution, but actually to be able to visualize what the geometry is. Right? So while he did have the solution, and certainly must have been a very brilliant student to do this, he didn't have really a good understanding of it. If you look at the acknowledgements of that paper, then he thanks some professor in Calcutta University or something. So the indications are that he must have been a student, probably at a presidency college or somewhere. And after that he just disappears. And the only reference I could find was on somebody's blog, so I don't know how reliable it is, which is that 2 years later, he dies in a botched hernia operation. So he exits, okay? And it would be useful, I've asked Biman and other people to know, one can probably track back who he was and what happened and so on and so forth. Right? Anyway, so that is another character who came and went. And this is Oppenheimer and Schneider. And after Oppenheimer and Schneider, we find another solution somewhere around 1942 or 43. And I particularly want to tell you a little bit about this solution because it was found by P.C. Vaidya. He is another amazing personality. So that will be the last story I'll tell you, and then I'll get on with some geometry. So this was, the Oppenheimer-Schneider was a ball of dust which just collapses and then forms a black hole. Vaidya's solution basically could be applied to describing the collapse of radiation, right? So just light mimicked as in some way or modeled in some way, collapsing under its own energy. Okay? Because in relativity, mass, energy are all, they all gravitate. And so this was a solution of light which collapsed. And actually what he did was that he found a solution of a radiating star in spherical symmetry. But around 90% of the work in general relativity is to find, in this game, is to find the right coordinates and the interpretation which simplifies the solution. And that Vaidya did for the radiating star. But very quickly, you can use the same coordinates and the same kind of things to write down a solution for a collapsing light beam, or collapsing what is called null dust. Vaidya found this in 1943 or so. So who was Vaidya? Just amazing guy again, He came from a small village in Junagadh, and he was very interested in physics and maths. So he moved to Bombay, where he studied physics and mathematics, got a degree, probably a bachelor's degree. Then he came back to Rajkot and he taught. So this is a beautiful documentary on YouTube, you should look at it. He taught in Rajkot, one of the colleges over there, but then I think the Maharaja took over, there were some differences with the management, and Vaidya quit. Vaidya was a Gandhian, and in fact in this documentary he says that in those days the fervor was such that embedded in his philosophy was always that given a situation, he would not look at how that situation would benefit him, but how he could turn that situation to benefit everyone. So that was the thinking. It was a different time in those days. So Vaidya now is, he doesn't have a job, although he's still tutoring, various people. He decides to join something which is called the Ahimsa Vyayam Sangh. So this is an organization which trains young people to be satyavradis and go and fight, in a non-violent way for the freedom movement. So he's doing that. This is around 1942, and the guy who starts this Ahimsa Sangh is a leftist. Right? And what happens in 1942 is Germany goes and invades the Soviet Union. And being of a leftist persuasion, this gentleman, the thought process is that an attack on the Soviet Union is a much bigger evil than tolerating the British. And because the British were the allied forces with the Soviet Union, said let's concentrate our efforts on the war, and so the Ahimsa was disbanded. Okay, so again Vaidya was wondering what to do, and he remembered that in 1937 he had attended a talk on general relativity by V.V. Narlikar, who was the father of Jayant Narlikar, who passed away recently, and he was fascinated by general relativity. So he wrote to V.V. Narlikar, who was at that time in Banaras Hindu University, and said, "Can I come?" V.V. Narlikar said, "Come." Neither from Vaidya's side nor from this side was there any talk of funding. So there was no funding. He went. It's all unbelievable. He went at the age of 24 with his wife, newly married, and a 6-month-old daughter. 6-month-old child. Went on a train, went to BHU, found a small room where they all stayed. 3 times a week he would go and meet Narlikar. Rest of the time he would try and do his calculations in his office or room or whatever it's called. And this was already 1942. This was the time of the Quit India movement. Right? There was a lot of stuff going on. And then there was violence. So Gandhiji called for the Quit India movement. I mean, I'm not a historian, so I don't know all the details. But basically, there was violence, some from the Indians, some from the, maybe even more from the British. And Gandhiji then went on a fast. So this was early 1943 probably. And Vaidya was extremely perturbed because especially, so every day he would get the local newspaper in Banaras and he would check on Gandhiji's health. And he was getting more and more agitated because apparently the 12th and 13th days of the fast were really, really bad. It was touch and go. So Vaidya was in his room, walking up and down, worrying about Gandhiji, looking at the paper, doing this, doing. Suddenly the Vaidya solution comes to him. 6 weeks, 6 days it takes. 1 week, he writes down the solution, sends it off to publication. And so that is a picture of this thing. So I don't know, I had a picture of Vaidya. So, Vaidya and another person who will appear but may not appear before 12:50, unfortunately, is Roy Chaudhary. Another amazing, absolutely amazing person. And those of you who are from West Bengal or from Presidency College or something would already, a legend. And there's also a beautiful documentary about him on YouTube, which I encourage you to look at. So this is Fortune, of course, in happier days. And this is Vaidya, as I saw him. So I would go to these Indian Association of General Relativity conferences, and Professor Vaidya would come. I remember he would wear a white glove. I think he would feel old. He was already very old. And he and Professor Roy Chaudhary would sit together. And like an idiot, so please take this lesson. I had just come back, joined as a faculty member in Raman Institute, and I was just too intimidated to talk to these people, right? So don't be intimidated, because you never know when the guy will pop off and you will regret it, and that you have never, ever had a chance to, talk to that person, right? So you must interact, you must talk to people, and these were such gentle and wonderful people. I really regret that I did not have, did not take advantage of that opportunity. Good. So, now all the solutions which they found were spherically symmetric, and I'll read out that so we don't blur it. And in all these solutions, the feature was that a black hole would form through spherical collapse of whatever matter or energy. And whenever the mass of the black hole, or whatever object, whatever was collapsing, was compactified into a size which is less than what is called its Schwarzschild radius, right? Then there was a black hole which would form. And the Schwarzschild radius is just, the units all come up, so it's proportional to the mass. Right? So bigger the mass, bigger the Schwarzschild radius. And all these solutions had a horizon at this Schwarzschild radius. Remember the horizon I showed you? So they have that horizon. And all of them had a singularity hidden at r equal to 0. Simultaneously, just a word about what happened in astrophysics. On the astrophysics front, around 1930, another fascinating guy, Chandrasekhar, at age 19, was on his way on a ship to take up a fellowship at Cambridge, and he was looking at other objects called white dwarfs, and he showed that white dwarfs beyond a certain mass would start collapsing. Right? Whatever were the nuclear forces there, as well as, we won't get into all that. Basically, if they were heavy enough, they would start collapsing. He didn't say what would happen after that. But he said white dwarfs beyond a certain mass are not stable, they will collapse. Now, similar ideas, which were into the field, were explored by Oppenheimer and Volkov on neutron stars in 1939. Okay? So they had a paper on neutron stars, which showed that neutron stars could further collapse, and that is really where black holes are formed, according to current wisdom. And this is what motivated Oppenheimer and Schneider to look for black hole solutions. So they were really looking. That probably stumbled on that, but they were actually looking for these solutions. And then there was the discovery of these objects called quasars, about which I know very little, but all the astrophysics people will know a little more. But they were basically, things which emitted huge amounts of energy from a very compact region, and the only source which people could think of was perhaps a black hole at the center. But the analytical work with all the singularity is something very strange, right? Everything blows up, your equations stop working, and you're done, right? So people are very uncomfortable with the idea of singularity inside a black hole, and all these solutions are exactly spherically symmetric, right? So everything had to be exactly spherically symmetric. Of course, in the real world, nothing is spherically symmetric. So people started questioning this and said, maybe black holes really don't exist, because this is all in exact spherical symmetry, and maybe this is unphysical, right? So now what did people do? Now, logical thing to do is to look at the Einstein equations and try and solve it for non-spherical distributions. But this is devilishly hard, and in fact, Feynman's advisor John Wheeler, who might appear later, maybe after 12:30, actually had a program of looking at Einstein's equations, trying to solve them, right? Then what happens is that, I don't know what analogy to use, but like a lightning bolt, this guy just comes from nowhere. Roger Penrose is not even a relativist; he's a mathematician. Okay, amazing. I mean, like after Schwarzschild, this guy is totally amazing. The kind of revolution he brought about in our understanding of general relativity is just, as I hope I will convince you. So what did he do? He was a mathematician, and in his interviews he also says that, I always try to bring a different view to the same problem, right? To look at it in my own way. So he said, forget these equations. Right? He himself says he's not good at solving all these equations, right? So instead of looking for non-symmetric solutions, which would describe this thing, he focused on what I started out with, which is the behavior of light trajectories in black hole spacetimes. And he noted that inside the event horizon of these known highly symmetric black hole solutions, there were spherical surfaces in which light was locally trapped. I'll tell you what local trap means. Now he called such surfaces trap surfaces, and while they were spherical symmetric, their definition did not involve spherical symmetry. And his genius was to realize that the existence of such a surface anywhere in your space-time directly implied the existence of a singularity to its future. Okay? And if in addition, now this didn't show you that there was a black hole, but if such a surface formed, which had nothing to do with spherical symmetry, you knew there was a singularity in the future, and then you just kind of speculated, and this is something which is unproven, that this singularity would be hidden behind a black hole event horizon. Just like for the other black holes, you can't see the singularity, it's inside the horizon. Similarly, so that is called the cosmic censorship hypothesis. It's not yet proved, but a lot of people buy it, and if you do, an exception is Pankaj Joshi. There are lots of, okay, I don't have time to say all these things, but basically if you have cosmic censorship together with what are called the Penrose singularity theorems, then you expect that black holes form, away from spherical symmetry, because trapped surfaces have nothing to do with spherical symmetry. He isolated something in spherical symmetry and gave it a prime, spotlight in his whole thing. Okay, so let me define these surfaces more carefully. I don't know how much time I have actually. Am I out or?
26.
20? Okay, so I'll just stop in 6 minutes. We'll just, whoever wants to talk to me further. Okay, so what is gravitational trapping of light? So you consider a sphere in this way, right? Sit on the surface of the sphere and shine light outside. So those light fronts will go on increasing in area, right? Alright, so those are called diverging light fronts. And if you shine them inside the sphere, then they will converge. Right? However, in a curved spacetime, this is our own flat spacetime experience, in curved spacetime, this behavior can change, and it can happen in particular that both the outward sets of light rays and the inward ones converge. Okay, it's very counterintuitive, but it's possible. And this is only a statement close by the surface. So close by, you shine the light space-time diverges. Here there are instances where it converges. Here as well as inside. So this is called a trapped surface. Light is locally trapped. And this is what happens close to a black hole. If you look at the light cone structure where both things are kind of falling in, it turns out that both sets are converging. So when the inward light converges and the outward light is just on the threshold of converging, so it's more or less collimated, the instantaneous outgoing spherical waveform doesn't change its area and the surface is said to be outer marginally trapped. So it's marginally trapped. Now the trapped surface is just local, right? You take a surface and you can find out whether it's trapped or not. Okay? Whereas the event horizon, it's something global because you need to know that light never gets out. Right? So you have to wait for the whole space-time geometry to be there to check whether all the light gets out or doesn't get out, is there an interior, etc. It's a very unphysical concept. You have to wait for all time to tell really whether you have a black hole or not. So I just wanted to say that. But technically a black hole is said to exist only if there is this event horizon. Okay. Now, this I have already said. In the last 3 minutes, I wanted to give you a little bit of an inkling about what this converse theorem is about. Okay? So let me try. I will probably, unfortunately, have to stop in the middle. 2 ingredients, forget the third one. Right? The two are enough to give you a picture. One is that you take a 2-dimensional closed surface and you look at all points which are reachable to it by sending signals, light signals or particles or whatever. Okay, that is called the future of this logical. You look at the boundary of this future. Okay, now because in that light cone, right? If you have time-like guys, right? Their boundary is light. Correct? I mean, if you look inside the light cone, the cone it's all light. So the boundary of the first thing you can show, just using geometry and topology, no equations, is that the boundary of the future of a closed spatial surface is ruled by light rays. Okay, that's quite reasonable. So that's the first thing. The second thing is the following. So if I look at the structure of this boundary, because it can certainly happen. It happens that even when you shine light inwards, that the light rays intersect, right? So now, if wherever 2 light rays intersect, they go on and intersect. That point is called a cross-stick. All right. And for a closed surface, what one can show is that if you have these 2 light rays here, which I've shown, right, on the boundary, and they intersect, then any point to the future, if you just extend this light ray, you continue on that light ray after it is intersected with this one, and you look at points on this light ray, you will find that you can always send a particle signal to such points. Is that clear? Whenever light rays intersect, you go further on one light ray, you can from the surface send an actual particle signal which travels less than the velocity of light to go over it. That is what topology and geometry etc. tell you. What does that mean? That means that that point cannot be on the boundary of the future. It has to be inside the future. Because the inside was all points you could reach by normal particle signals. What does that mean? That means that as soon as 2 light rays cross, they both exit the boundary. Fine? Now, when light rays can cross, that is dictated by curvature and the Einstein equations. Alright? That topic is called the focusing of light rays. Okay. Now recall that in Newton's theory, it's an attractive, gravitational force is attractive. In Einstein's theory, the role of attraction is that the curvature is such that trajectories focus when there is matter. That is the when you see the attractive nature of gravity. So there is what Roy Chaudhary showed is that if you have positive energy matter, and if you have particle trajectories which traverse this positive energy matter region, they will start focusing. Okay, so that is Roy Chaudhary's contribution. Later on, I think Schneider and Penrose independently showed that not only particles but even light rays they would always converge, right? And if they were initially converging, right, then in finite time, they would intersect. Alright? So you have positive energy matter. If you are initially converging light rays, then in finite time they would intersect. And so Penrose's amazing insight was to realize that what if this surface was a trap surface? If this was a trap surface, then all light rays going out from it would be converging. Right? Then the Roy-Choudhury equation or whatever went, there's only positive energy matter. So what can happen is these light rays can only focus more. And because of the theorems, not only will they focus more, they will all intersect each other in finite time. So that is rather bewildering when I draw the next picture, because it tells you that, see, this is in flat space-time. Think of this as a sphere rather than a circle. So you have inside inner light rays, okay, they will converge. The outer light rays will just go on, right, forever and ever. The future is infinite. But look at this guy here. This is a trap surface. So the ingoing ones in red will converge, but the outgoing ones are also converging, right? And so all the particle signals you can send can only be inside this. It's totally weird. You're shooting a bullet, and that guy is somewhat trapped, right? It cannot exit this place. You understand? I mean, that is the power of this whole thing. It cannot exit this place because that is the boundary of the future. And if it exited, that point would be in the interior. So it cannot do that. It has to be confined here. That's totally weird, right? And that exotic weirdness can be then pushed forward into an argument which says that somewhere in this future there has to be a singularity, a place where the life of these things just ends. Okay? So that is Penrose's singularity theorem. I have no time to tell you about the connection, the mysterious connection with thermodynamics which Bekenstein found, nor about Hawking radiation. But let me just say two things and complete the Penrose story. So Penrose showed that if a trap surface formed anywhere in space-time, singularity would definitely form in the future. If in addition cosmic censorship holds, singularity would be hidden behind an event horizon and signal the formation of a black hole. Okay? So what is the lesson of all this? And I'll tell you that lesson and then please you can go. Okay? It was a very nice lesson. The lesson, of course, you should have understood by now is that walking is good for research. So you remember that Vaidya also was walking furiously, right? When suddenly this thing came to him. This is a quote from Penrose from an interview after he got the Nobel Prize. At that time, so which is when he got this idea, I was at Birkbeck College and a friend of mine, Ivor Robinson, and who's also a famous relativist, who's an Englishman, but he was working in Dallas, Texas at the time, and he was talking to me. I forgot what it was. He had a wonderful way with words, and so he was talking to me, and we got to this crossroad. And as we crossed the road, he stopped talking as we were watching out for traffic. We got to the other side, and then he started talking again. And then when he left, I had this strange feeling of relation. And I couldn't quite work out why I was feeling like that. So I went through all the things that had happened to me during the day. You know, what I had for breakfast and goodness knows what. And finally it came to this point when I was crossing the street and I realized that I had a certain idea, and this idea, what the crucial characterization of when a collapse had reached a point of no return without assuming any symmetry or anything like that. And this is what I call a trapped surface. And this was the key thing. So I went back to my office, sketched out a proof of collapse theorem. Just like 6 days there, got it. The paper I wrote was not that long afterwards, which went to Physical Review Letters. It was published in 1965. I think this is the paper which got it the Nobel Prize. Okay, the single paper. So that is basically what I can do with the time available, and let me just I think we can just conclude over here. So I think, I hope that black holes, I've convinced you, are really fascinating objects, and I could not tell you really about the connection with entropy and thermodynamics, but let me just read this out. So even as late as the early 90s, when I was doing my PhD, people were not sure how seriously to consider classical black hole solutions as realistic. Even in 1990s, I remember. Now black holes are everywhere, right? all over the place, right? Center of galaxies here, there, rotating, collapsing, all sorts of things are happening. The evidence for the existence keeps coming up. The strongest evidence, in my opinion, is from the detection of gravitational waves by LIGO. No time to tell you about that. The second thing I didn't come to, Bekenstein's work reveals a fascinating connection of the black hole area of the horizon with a completely different subject, which is thermodynamics. Now, how the hell is GR related? It's completely mind-boggling. Hawking's work on the quantum properties of black holes shows that not only could black holes have entropy, which is a thermodynamic quantity, but they were also hot objects, and they could radiate. Now, classically, nothing can escape a black hole; it can't radiate, but quantum mechanically it can. There are ensuing puzzles I didn't have time to tell you about. These are of the microscopic origin of black hole entropy and what is called the information loss problem. And these, of course, challenge the imagination, invite curiosity, and they perhaps serve as rare theoretical tools in our ongoing search for a theory which can combine quantum mechanics and gravity, which is the outstanding problem in fundamental physics today. So thanks a lot for your attention, and thank you very much.
Sessions, you can have a talk with them outside. And I would like to invite Dr. Gitanjali to present a memento on Sri's vehicle as a token of graph.
Thanks a lot.
Thank you.
Yeah, I'll be next door. I'm joining DU Physics department after Diwali.
I request everyone to move outside for the refreshments, and we'll also be having some photographs.
Also, I have to take a